Welcome to the last task, that is shellcraft, and we'll basically be rooting the machine by making it follow our own instructions. Take note though, you want to spin up the machine and SSH into it and work from there, otherwise you might be rooting your own VM and that might break it. I have not tried that and you shouldn't either. First thing we need to know is ASLR, address space layout randomization, which randomizes where in memory the executable is loaded each time it is run. Like Pi, it makes attacks that rely on memory layout more difficult. So basically the fun is that since there's no print flag function to jump to like we were doing in other tasks, we can make the code follow our own instructions. Variables are stored in memory just like the program itself, so if we write instructions in our variable and direct the EIP to it, we can make the program follow our instructions. And remember that the EIP is the instruction pointer. This injected code is called the shellcode because it is traditionally, but not always, used to spawn a shell, right? What we need to do first is make sure we can control the EIP, and then we'll do that by finding this location by first filling it with 0x deadbeef and hex like we had been doing it in previous tasks. So let's fill the EIP with deadbeef first, and then we can move on to the other things. So what we'll need to do is make our cyclic pattern like that. And then we shall spin up GDB on our binary. We run that with our pattern. And as you can see, the EIP is filled with TAAA. And if you remember from previous tasks, that is task 3. If we copy this code, we'll be able to fill the EIP with 0x deadbeef. So we will nano this and call it an exploit.py, copy and paste that. So all we need to change is this value that we're supposed to find. Instead of JAA, this time is TAA. So I'll save that with Control O and then press enter, and then Control X to exit. And we shall spin GDB up right after we direct this to an attack file. That is the wrong command. Okay. Run that with attack. And as you can see, our EIP is filled with 0x deadbeef. Okay, let's move on. We might need to answer the first few questions before we do that though. What is ASLR? I do not want to type, so I'll just copy and paste that. Address space layout randomization. Who owns intro? Okay, so let's quit out of GDB, ASLR, and that is root. That's interesting. Use checksec on intro to poem final is NX enabled. Checksec. Okay, that is not going to work. File equals intro. I cannot be bothered to type today. And NX is disabled, as you can see. So we'll put an N. Please use cyclic tool and GDB to find the EIP. What letter sequence fills the EIP? So like we found out just a few moments ago, that is TAA. Okay, we have not reached this step, so let's go up and read a bit. Okay, once we control the EIP, we need to direct it to the stack where we can place our own code. The top of the stack is pointed to by the SP, that is the stack pointer, which is called the ESP in 32-bit machines. For me, the ESP is located at 0x yada yada yada. One thing I forgot to mention is that we're supposed to disable ASLR, and there's a script we're supposed to run to do that, and we're supposed to run it with sudo privileges, I guess. No, it worked. There we go, it worked. And so now we don't have ASLR enabled, and we will not get random addresses every time we run our binary. Correct? So we have to find, where were we? And you can check the location of yours in GDB. We have to find the location of the ESP. That is the stack pointer. So let us do that. We run this. We can run this with pattern or attack. I'm just going to use pattern. and this is the location of the ESP. You can copy that, you can find it here or here, it's the same thing. So once you found the location, if we want to jump to our shellcode, we want to jump to the middle of the stack. So we usually add an offset to the ESP location. In your exploit, I use an offset of 200 because that's what ended up working for me. In other challenges, you may only need an offset of 8 or 16. I found that choosing the right offset is a matter of trial and error. So we have our stack pointer and then the offset of 200. You may be wondering how we're going to point the EIP to our shellcode. And the answer to that is to make our variable into a big landing spot. There's an instruction in assembly called the no-op, which is 0x90 in hex. And the no-op is a space holder that passes the EIP to the next space in memory. If we make a giant landing pad of no-ops and direct the EIP towards the middle of the stack, odds are that the EIP will land on our no-op pad, and the no-ops will pass the EIP down to eventually hit our shellcode. This is often called the no-op slide or slid, because the EIP will land in the no-ops and slide down to the shellcode. In my case, a no-op slid of 1000 worked, but other challenges may require different sizes. When writing a raw hex byte in Python, we use the format \x00, so we can write \x90 for a no-op. So this is our no-op slide. Before we write our shellcode, we can inject a breakpoint at the end of our no-op slide to make sure the slide works. The breakpoint instruction in hex is 0xcc, so we can add the following to our code. Our payload should be as follows. Please direct the output of this to a file. So we need to fix up our exploit, it seems. Okay, we have this. We don't have the no-op. Okay, let's quit out of GDB and we will nano our exploit. What we need at this point, okay, my bad, is the address. Let's copy that and then nano. And then I will put that as a comment just to save that here. So our EIP, let's copy and paste this. Control K to delete lines. Paste that there. And put the address of the ESP here. What's next? We have the no-op slide. And then our shellcode with the breakpoint \xcc. And then our payload should look like that. Copy and paste this. And then we print the payload. So we can save this. And then direct the output of this to attack. Okay. If we input the text file into intro to Pwn, we should hit a breakpoint. Please answer question 5. So where is it? Question 5. Run the exploit with the breakpoint outside of GDB. Okay, what does it say when we hit the breakpoint? So we are supposed to run intro with attack, and it says trace /breakpoint trap core dumped. I think that is what it says. Don't think we'll need that part. There we go. Got the right answer. Great, we can inject our own code into the program. Of course, we want to do more than just hit a breakpoint. We want to spawn a root shell. That means we need to write some shellcode. While some crazy people like to write shellcode from scratch, Pwntools gives us a great utility to cook up shellcode, and that's called shellcraft. If you have ever used MSFN, shellcraft is a similar tool. Like cyclic, shellcraft can be used in the command line and inside Python code. I like to use the command line and copy and paste the shellcode over to my exploit script. So shellcraft, this is for a basic bash shell for Linux executables with i386 architecture. A neat feature of shellcraft is that we can print our shellcode in different formats with the TAC-F flag. The possible formats are listed if you enter shellcraft TAC-H command. Please answer question 6. Okay, it says run this command. Copy that, which will print out shellcode in assembly format. The first line will tell you that it is running a function from the Unix standard library. What is the function it is using? Okay, so let's run that. Might need to clear my screen a bit. Make that bigger. So the first line, it's using execve. Okay. We have answered question 5. Question 6 rather. There's a big snag. There's a bit of a snag in the above shellcode. In order to get a root shell, we need to keep the privileges of the intro to Pwn final, although bash will drop the privileges unless we add the tag p flag. If we observe the assembly code for this shell, we see that it uses execve and passes bin sh as the first parameter and sh as the second. The first parameter is the path to what we want to execute, and the second parameter is the argv array, which contains the command line arguments. In this case, we want to execute bin sh, but we want to pass sh and tag p into argv array. We can use shellcraft to create execv shellcode with bin sh and sh tag p as parameters. We can do this with the following command. Okay, let's try run that. There we go. That is assembly shellcode. Interesting. We can run this command. When we run this command, we see it is the same as the linux.sh shellcode, except the added tag p to the argv array. To write shellcode that is easier to use in our Python exploit, we can replace the tag fa with tag fs, which will print our shellcode in string format. We can copy that and paste it into our exploit, replacing the breakpoint instruction. Our code is almost done. Until this point, we have been printing our payload and manually inputting it into the executable. Like in the networking task, Pwntools allows us to interact with the program automatically for a local process. When we run this command, we see it is the same as the linux.sh shellcode, except the added tag p to the argv array. To write shellcode that is easier to use in our Python exploit, we can replace the tag fa with tag fs, which will print our shellcode in string format. We can copy that and paste it into our exploit, replacing the breakpoint instruction. Our code is almost done. Until this point, we have been printing our payload and manually inputting it into the executable. Like in the networking task, Pwntools allows us to interact with the program automatically for a local process. We use the process function. So proc equals process and then our binary. We can receive data from the process, and since the process sends data with a new line, we can use the receive line rather than the receive in. After we have created our payload, we can send it with proc.send payload. Finally, after we have sent the payload, we need a way to communicate with the shell we have just spawned. We can do that with proc.interactive. So to recap, our whole Python script is this. So I'm just copy and paste that. No shame at all. Clear my screen. Nano my exploit. And I'm going to put this at the bottom, because there's something I'd like to copy and paste as well. So if you remember, we have the address of the ESP that we need to copy. So we should copy that and put it here. And then from there, we can remove everything that we don't need. So Control K to delete lines. And that is it. This should give us a shell. Save that. Alright, that was a lot. Take a deep breath and run our Python code. Alright, okay. Run who am I once you have the shell. Okay, fingers crossed our exploit actually works. Who am I? That didn't work. Who am I? Oh, we are root. ls. We can cd into /root. ls here, and we can cat the flag. And we are done. That is it. We have completed intro to Pwntools. I hope you enjoyed the room just as much as I did.